Hey guys, it's May 14th. We looked at the 3 types of pressure problems you need to know for the condensed test. First thing we have here is basically a model of a hydraulic jack. You have a big area piston here, a smaller area piston here. I've noted those as A1 and A2 for those 2 areas. If we put a car on top with mass 1,000 kilograms, we can find the force of gravity on that car, which will be then the force 1 on this area 1. If we wanted to, we could find how much force we would need to put on this piston to lift the car. We didn't bother, we just looked at how to get the formulas. So what you need to realize is if you have a hydraulic fluid in here that's not compressible, the pressure is the same everywhere. So you can write that pressure 1 is equal to pressure 2. And then from your knowledge of what pressure is, that it's a force per unit area, you say pressure 1 is force 1 over area 1. You say that pressure 2 is force 2 over area 2. From that, we can play some checkers here. We can make 2 equations. If we want to know what force 1 is, well, the only thing that's impeding that right now is this A1 right here. So you move it up diagonally. So it's going to be F2A1. Which we have here, F2A1, and the A2 is still on the bottom. So that's if you want to find force 1 and you have all the other ones. If you want force 2, which is kind of what we originally said we'd be solving for, well, here that is, same idea. You can rearrange both of these equations to find area 1 and area 2 just by switching A2 and F1. So the A2 goes there, F1 goes to the bottom. Pretty simple. Okay, so there's your 4 formulas, the only possible formulas for this situation. Okay, next situation. We've got a ship or a boat underwater. You have the density of water. You have the atmospheric pressure up here is 101.3 kPa, which is 101,300 pascals. If you want to find the actual pressure on the ship that's underwater, the atmospheric doesn't actually add that much. It is a tremendous pressure, but 400 meters under the water, the pressure you're getting is pretty tremendous. It's 3.9 million pascals right there. So the 100,000 pascals, it doesn't add that much. We still account for it though. So you take density of water times gravity times height, which is really the distance below the water. By the way, this does not work for atmospheric pressure problems, meaning you can't take the height of air above you and use this formula because gravity changes with height above the earth. And the other thing is the air compresses closer to the surface of Earth because there's more pressure on it. So this only works for non-compressible fluids.
Teachers, please submit your attendance now. That's all teachers. Please submit your attendance.
Okay, so you multiply those, you add the atmospheric like I did here, you get your overall pressure. One more problem. You've got a manometer. Okay, which is a U-shaped tube. We filled it with mercury this time. This is when both ends are open. If I put a vacuum on one side, I could also put a pressure like an air tank and apply some pressure here, and it would make this go down and this go up. Same difference. You still calculate things the same way. In your book, it will say something about a static pressure head for this problem. Here's your height difference between the levels. Here was the level before they moved. You take the density of mercury. It's the same as the previous problem, same formula. P equals dGH. Except this time the H is the height difference. And all you have to do at this point is convert that to meters before you put in the equation. You get that the pressure difference is 13.6 kilopascals. That is all.